Okay, I guess it's about time to get started. So last time we talked about, I guess we can still go back a little bit. We talked about the convergence and the properties of continuous and Fourier series. Okay, and here's a table, so summary of the properties. There are a lot of properties. They are very nice. There are linearity. And you can see when you do various operations with your signal, like time shift or conjugation or time reversal, there will be they usually have a very simple consequence on the corresponding Fourier series coefficient, etc. Okay, and today so we'll cut the review to be a bit short because today we are going to go to quite different thing that's I guess it's very similar, but not continuation. So we are going to go to the Fourier series representation of a discrete time periodic signal. So we'll be talking about Fourier series representation for continuous time periodic signal, and so basically we are going to do the same thing for discrete time periodic signal. And so this will be much faster. So we spend like 2.5 class to talk about continuous case, but it's very similar in discrete case. So I'm hoping to finish everything today, but let's see how far we can get. Okay, and anyway, so they are very similar, but there is still some difference we are going to see very soon. Anyway, so we start with what do we do for the continuous time case for and so that is we write our periodic signal. So we have a periodic signal x of n equal to x of n plus big N for some period big N, and we want to express it as harmonically related complex exponential. Okay, and so it's this is very similar to what we write down in continuous time. We write x basically just change t to n in this expression. So x of n equal to sum over k different k for this different harmonic index k. So a sub k e to a jk omega naught n. Okay, and omega naught will be 2 pi divided by n. N is this period. Okay, so this is similar to what we write in continuous time. And up here we have a little bit of discussion that's saying that it's a bit funny. Okay, so it says that we have the same motivation before. We want to express our x of n as a linear combination of the eigenfunction of your LTI system. And the eigenfunction is of the LTI system. We wrote them as z to the n. And but so this is a bit different than this complex exponential, but for Fourier series, actually complex exponential are nicer expression. So we translate z to the n back to e to the jk omega naught n. Okay, so we say if z is this purely phase thing, so z is the e to the jk omega naught, then we'll have z to the n equal to e to the jk omega naught n. Okay, and so we focus on those eigenfunctions that can be expressed as this complex exponential with purely imaginary exponent. Okay, so it's kind of for now it's not clear why we want to write z to n, but anyway, because we translate z to n back to e to jk omega naught n. And anyway, we focus on decomposing our signal into this linear combination of e to jk omega naught n. Those are the harmonically related discrete-time complex exponential. And so here is a review slide for what we have in chapter 1. So harmonically related discrete-time periodic exponential signal. So there are those e to the jk omega naught n, where omega naught is 2 pi divided by n. And k is an integer, and so far it's the same as continuous time, but a very different thing happened in discrete time is that we find out that k cannot increase infinitely. So if you increase k enough, it actually give you back the same signal, because we are only sample our signal at those integer points. So if your complex exponential is oscillating too fast, then those integer points don't actually see the phasor oscillation. So what happened is that in terms of k, psi k and psi sub k and sorry, it should be called phi. So this phi sub k and the phi sub k plus big N will be actually the same signal in terms of a discrete time signal. And so there are only big N different discrete signal. So okay, so there are only big N distinct signals, and you can choose how you want to label those big N of them. You can label them from 0 to n minus 1, or like minus n over 2 to plus n over 2, etc. I guess it should be minus over 2 plus 1 something. But anyway, yeah, so we have this thing, so that our summation k here is a bit different from continuous time. So from continuous time case, this k is summation from minus infinity to plus infinity. But now, since most of the k are the same, we don't need to sum over k from minus infinity to plus infinity. We only need to sum over the different big N terms. So consecutive, big N consecutive integers. Okay, so maybe 0 plus to n minus 1, or like 1 to n, etc. Okay, so the summation here, we have k only sum from this big N notation, means we sum over yeah, n successive integers, okay, or n consecutive integers, okay. And yeah, so we have some example. Maybe you sum from 0 to n minus 1, or you sum from 3 to n plus 2, or 1 to n, or even minus 1 to n minus 2, etc. Okay. And yeah, so this is the first difference to continuous time case. So this is, if you remember, this is the synthesis equation now. So this is if we have a linear combination of those harmonic related periodic exponential, is going to give you another periodic function with period big N. And the only difference is, instead of summing OK, you summing over k in those bracket big N. Okay. And then we see the second difference. Okay, so we now have the synthesis equation. We want to get the analysis equation, and analysis equation is much easier to get now, because if you think about this transition between x of n and ak, so you see that, well, x of n is a periodic function, right? So you only have it's basically specified by n values, because it has period big N. Okay, so you have big N different values for your x of n is x0 to xn minus 1, and now you have this synthesis equation. You just write down. If we give you, so for every x of n, so it's from x0 to xn minus 1, you can write down this synthesis equation. And you can just think this synthesis equation as a linear combination of your ak. And as we see, ak also only have big N different numbers, because we know that, say, ak equal to ak plus big N, because this harmonic k equal to harmonic k plus big N. Okay, so ak equal to a plus big N, and we only have big N over the different ak, so a0 plus n. a0 all the way to a minus 1, a sub n minus 1, and yeah, so you can write down those set of linear equations. So x0 equal to a0 plus a1 plus all the way to a n minus 1, and x1, you write this out, and it will be a0 plus, well, e to the a0 plus e to the j2 pi 1 divided by n. So this is e to the j omega 0. I guess I should write omega 0 here. This is e to the j omega 0 k. Okay, so this is e to the j omega 0 a1 plus e to the j omega 0 k equal 2. Then it will be times 2 and times a2, etc. etc. Okay, and so you see that each one of them is basically a linear equation in terms of those variables a0 to a n minus 1. And it's very easy to verify that this set of equations are linearly independent, so that if you want to solve for those a0 to a n minus 1, you just invert those linear equations. Okay, so you have an equation with n unknown. Those n unknown are your ak, so a0 to an minus 1. And yeah, so you just solve those linear equation and you can find your a. Okay. And yeah, so you can solve your AK this way. It's a bit different than the way we get a synthesis equation before. But this is not how we are going to get our synthesis equation. Actually, we are going to do a similar thing. So let's pick a peek a little bit. We are going to do something very similar to how we get our analysis equation before, just like in continuous time. But what we see here is that from this conversion, we see that this x of n, and x of n, and s of k is basically unvariable to unvariable linear transformation. And this tells you that this discrete-time Fourier series representation, this transformation between x and a is just a linear transformation, and you can transform them back and forth arbitrary for arbitrary x and arbitrary a. And the important things here is that there is a non-convergence issue, okay? Because the transformation between x and a is now just a linear transformation. And so this tells us that for any single x or any set of coefficient a, there is no convergence issue, okay? No convergence issue, okay? So the Fourier series representation for discrete-time signal is always converging, and the transformation back and forth is exact. It's just a linear transformation. We'll see more example later. Okay, so that's the second difference to continuous time case. There is no convergence issue. Okay, and but let's go back to trick. So we had our synthesis equation here, and now we derive analysis equation. And this is very similar to what we do before. So basically, we are trying to do kind of inner product with different vectors. Okay. But anyway, so what we do is before we will multiply e to the minus minus n omega naught t, and do integration. And now we are doing similar thing. We are doing multiplying this e to the minus j r omega naught n, and summing over one period. Okay, so before we were integrating over one period, now we are summing over one period. And we multiply this e to the minus j r omega naught n, because we think that this thing will pick up the R's amplitude of our synthesis equation. Okay, so this thing will pick out the R in those e to the jk omega naught n, because we have this kind of orthogonal relationship. So we have that if you sum over n, and then you sum over this complex exponential e to the j and some k minus r number times omega naught n, where omega naught is 2 pi divided by n. And so you sum over this thing, then this thing is n if your k minus r is equal to 0. And this big N here is very obvious, because you are summing over a whole bunch of 1. This complex number is 1 if k minus r is 0. Okay, it's 0 over a period of n. Okay, and now the interesting thing here is that if this k minus r is not multiple of n, then you are summing over, so what is this thing? So you are summing over e to the j omega naught n times e to the j omega naught n times this k minus r number. You are summing over this e to the j k minus r times omega naught and to the nth power. And so you can think about this is actually summing over things in, so that we have kind of a sketch here. So this is a complex plane, and then you have e to the j omega, you have e to the j something here. So this is a purely phase, so those are points on your unit circle, and those points are basically evenly spaced out point on a circle, because you can think this this point is e to the j 2 pi times your k minus r over n. Okay, and then the next point will be this point times 2, because so you have n equal to 1 here, then n equal to 2 here, because you have n equal to 1 here, you have this angle, then by the polar, and think about this as a polar expression of a complex number. So when n equal to 2, then you have the angle being twice, and when n equal to 3, the angle being 3 times, etc. So you are summing over those integer multiple of those angle. And you also know that when small n equal to big N, you will come back to the 0 point. So when n equal to 0, you are at angle 0 at this 1 point. And when small n equal to big N, you will go back to this point. So you see that you're summing over those big N bracket points. So summing over, say, 0 to n-1, then you are summing over those equally spaced out points on the circle. And then here, so we give a high-level argument. Because you are summing over those evenly spaced out points on the circle, then by symmetry, the average of them should be just 0. Okay, because they are, by symmetry, they are evenly spaced out through this circle. So you sum over all of them, it will be 0. Okay. And and we have a more detailed derivation of this fact here. But this is a high-level idea. You sum over those complex faces, and if you sum over, if the angle here is non-zero, then you sum over these equal distributed points on the circle, then it becomes 0. And if the angle is actually 0, then you are summing over a whole bunch of 1, and you get bigger. Okay? So this is like a second relationship we need to use. Okay, if you're okay with this, then the rest of the derivation is pretty straightforward. So so we multiply our x of n with u or e to the minus jr and omega n, and summing over 1 period big N, and then we use the synthesis equation to write out our x of n. So it's some k e to the jk omega n, and then it's k and the minus r combined together to get our k minus r. Okay? And we change the order of summation, so we deal with sum n first. Then we have this sum n e to the ak doesn't depend on n. So sum n then e to the jk minus r 2 pi divided by big N times small n. So it's exactly this thing. Okay? And so we get this thing exactly. The right hand side becomes this, so sum k ak, and this thing. And then we know this thing is big N if k minus r equal to k minus r equal to multiple of big N and 0 otherwise. Okay, and so we write it here. So it's this, and so if we choose r as a value over okay. And now we need to choose R. So if we choose R inside this n bracket, then we will get that. So if R equal to n bracket, then k minus R can only be 0 or otherwise, right? Because they cannot be more than plus minus n difference. Okay. So if your R is so basically this line want to say R in n bracket. R in this n bracket, that's the same as this big n bracket. Okay, so if R is in n bracket, so either you have R equal to K or this summation equal to 0. Okay, and either R equal to So here we have K here, right? So either R equal to K or the summation equal to 0. Okay, and And so this thing is saying that, in other words, but R is a fixed value, so basically we need to say K need to equal to R. Okay, so K must equal to R, or otherwise this thing is 0. Okay, so here what we get is just big N. So this part will become big N, as we say, and when K equal to R, so we got AR. So this side become bigger N times AR, okay? Because this summation will pick out the K that's equal to. So this thing is a function of K and R, and it says k must equal to r, otherwise this is equal to 0. And so you pick out the k that's equal to r here. Okay, so yeah, so if r is yeah, okay, and so that's how we get here. So this is basically our analysis equation. We see that to get the AR, we just need to do this summation. You put n to other side, big N to other side, then we have 1 over big N, this thing equal to AR. And then you can just change R to K, so you just rename R to K, then you have your equation for AK. Okay, and but before that, let's do some comparison to the continuous sum case. So hopefully this don't confuse you more. Okay, so in continuous sum case, we have this kind of orthogonal relationship. We define inner product between two complex exponential function e to a j n omega t and e to a j k omega t as this integration over one period, and e to the actually I write n minus k, but anyway I write k minus n here. K minus n omega t dt. Okay, and yes, and this integration we see that is 0 when k not equal to n, because it's like integrating over this sinusoidal oscillation, and it's t when k equal to n, because it's like integrating over the constant function. Okay, so this is t times delta n minus k. So only when n equal to k, this thing is 1. This thing is big T, otherwise it's 0. And in the discrete case, this is a derivation we just say, or the thing we just argued. So we have now we have the inner product between those discrete functions. So we define this inner product between this discrete function as also summation over one period, and yeah, and the multiplication of each term with some complex conjugate. So yeah, yeah, so this is actually correct. So summation e to a jk minus r omega n. And as we say, this thing is very similar to this thing before, so equal to big N when k minus r equal to 0 multiple 2n, and 0 otherwise. And you see that so here we are being a bit different than continuous time, because k minus r equal to multiple of big N is still give you this non-zero value. This reflects that the harmonics for discrete case is periodic with period big N. So you change k to k plus big N, then you should get the same number here. And anyway, so you see that this is very similar to the period times delta k minus r, but I only write approximate sign here because k minus r can also be so this is not actually delta, this is actually what we call impulse train, as we say later. So this is like when k minus r equal to big N, then it's non-zero. So it's like for every big N you have a non-zero value. So it's this function. So its height is big N, and the period here. So this is like a periodic impulse. Okay, so a periodic impulse with period big N. Okay, so it's this function here. And anyway, so this is a continuous case, discrete case, and if you want to do the and we have a high level argument in picture here. So continuous case, if we say integration over this oscillation in one period or two period is 0, and in discrete case we are saying that we sum over those equally spaced out points on a circle is 0, and when k equal to n or r equal to n or r equal to k is either integration over a constant function or a summation of a whole bunch of 1, and you will get non-zero value. Okay, and so if you want to see a detail, if you want to see the formats, I think it's in very detailed, so I'll skip it here. Okay, but you can brute force do the integration when k not equal to n, and it was this thing before we had done. And you can also do brute force summation when k not equal to r plus multiple of n, and you can do the summation of it will be summation of geometric series, and I guess you can either just write down the summation, or you can use the geometric series formula to do the summation, or you can use some symmetry. Here we give some symmetry argument basically saying that you are summing over those points that are on a circle, then you sum over all those things multiplied by the same face is going to give you the same thing. Then the summation equal to, so if the summation called A, and then the summation, then the same A times the sum face value equal to this thing times sum face value, right? And because then you move things around, then you see this face value small a times minus 1 times your big A equals 0. But you know your small a is not 0. Small a is your e to the small a is this thing, your e to the jk minus omega naught. And so this first term is not 0, so you know the second term is 0. Okay. This is some symmetry argument saying that you rotate also 3 points, and adding them together is same as adding those 3 points. But this rotation is non-zero phase. This rotation is not equal to 1, is some face value. So that means your summation must equal to 0. Okay, or you can also use the brute force geometric series formula, and you should get the same result as the summation is 0. Okay, and yeah, so anyway, so we now get our synthesis equation and analysis equation for our discrete-time Fourier series. Okay, and that's just because they are the most important equation for this subsection, so let's read through them once again. So synthesis equation is an equation that tells you how to get x of n from a sub k. So x of n equal to summation k in one period, ak e to the jk omega naught n. Or it's the same thing, you can also write omega naught as 2 pi divided by big N, where n is the period for both the ak and x of n. Okay? And the analysis equation tells you how to find the ak from your x of n. It says ak equal to 1 over n, summation small n, also in a big N interval, x of n times e to the minus jk omega naught n. And just like before, you can write omega naught as 2 pi divided by big N. Okay, so that's synthesis equation and analysis equation. Now, and you see that they are very symmetric, except that one of them don't have 1 over n, and this has 1 over n. Okay, it's basically the same thing if you think ak as a of k, as a function of k. Okay, and as we say, this big N means that interval of length big N. Okay, so it's from some n0 to n0 plus big N minus 1, and n0 can be anything. And maybe most natural peak is n0 equals 0, and they are summing from 0 to n minus 1, and ak also 0 from to n minus 1. Okay, and yeah, so these two formula will tell you everything you need to know about discrete-time Fourier series. I mean, you can do any calculation from those two equations. Yeah, but first let's be more property. So as we said before, so because we are not discrete time, we have this extra property that ak is also periodic. AK is also periodic with period big N. Okay, and yeah, because we think k is ranged from arbitrary big N interval, then instead of thinking ak only defined on this interval, we can extend the definition of ak to be just a periodic function. So yeah, so this is a thing happen also only in discrete case. That is, ak is periodic with period big N, and I guess this is yeah, go back to the fact that we have in chapter 1 saying that the frequency is periodic in I guess the frequency is periodic with period 2 pi, right? In chapter 1, we say that we think about the discrete time function. This I guess it's already here. So this e to the jk omega n. This is related to e to the jk omega n is those harmonic exponential is periodic with period big N, because you change k to k plus big N, it's the same function. So we think the coefficient for this e to the jk omega n is same as the coefficient for this e to the jk plus big N omega n. Okay, and this is go back to the fact that for the discrete time case, e to the j omega n equal to e to the j omega plus 2 pi n. Okay, just a little bit of connection. So yeah, so it's kind of from this fact we got this fact and got this fact. So in discrete case, because we only have a sample point and an integer value, then e to the j omega n equal to e to the j omega plus 2 pi n. And then in terms of harmonic, this means that the increase k to k plus big N is the same harmonic, and then so the coefficient of the harmonic should also be the same. So coefficient for the kth harmonic, we define it as the same as the coefficient of the k plus n's harmonic. Okay, so this is for discrete case. And so that's the first difference. And the second difference, as we say, there is no convergence issue for discrete time Fourier series, because, well, this is basically just we write it in a very complicated way, but this is basically just a linear transformation back and forth. So we have a big N of those x of n and a big N of those a sub k, and so we can write a linear transformation back and forth. Okay. And if we are all okay with this, then let's go to see some example of discrete Fourier transform. Okay, and so first we have x of n equal to sine omega n. Okay, so I guess this is a very easy case where we don't even need to really need to do this summation. Okay, we don't even need to use the analysis equation to do summation. Okay, we can just break this sign equal to complex exponential. And anyway, so x of n is a periodic function, and we have our omega n equal to 2 pi divided by big N. Okay. Remember that we also have issues with also need to have our omega n being specific value for x of n to be even periodic for discrete case. And you see here is is a rational number. This is 1 over big N times 2 pi. So this is actually periodic, and its fundamental frequency is fundamental period is big N. Okay, and okay, so it's periodic with period big N, and we can write it as just the sum of complex exponential. So, or linear combination of complex exponential. So 1 over 2j e to the j omega n minus 1 over 2j e to the minus j to omega n. This is just our reverse order. And yeah, so from here we can just read. So this is coefficient a1 for e to the j times 1 times omega n. And here we have coefficient a minus 1, because this is minus 1 times j omega n. And the coefficient a minus 1 equal to this minus 1 over 2j. Okay, and ak should equal to 0 for all other k, because they are just not here. Okay, and also ak equal to k plus n. So we can plot our ak in a line, then it will be a periodic function. So for a1 is 1 over 2j. Okay, so this is plotting ak as a function of k. And a1 is 1 over 2j, a minus 1 is minus 1 over 2j, and so this thing should be periodic with period big N. And to plot this, we need to know big N. And here we plot this assuming big N equal to 5. And so you see that for every 5 of them, it should be periodic. So this minus 1 should equal to 4, should equal to 9, and it should equal to minus 6, etc. And this a1 should equal to a6, should equal to a11, should equal to a minus 4, etc. And I guess something to say here. So we think about this x of n equal to summation ak equal to jk omega n. Then this range of n, you can pick any interval here. So you can pick an interval, say from max 2 equal to 3. Then you will sum over this a minus 1 and this a1. Or say you can pick the interval from 0 to 4. Then you will have this sum with a term, summing over a term of this a1 and a term with a4. But we will know this a4 term equal to this a minus 1 term, etc. Okay, so you can also kind of see from this picture, you can pick arbitrary n interval to sum, and you will summing over 1 of the a1 and 1 of the a minus 1, and the result is the same x over n. Okay, so that's an easy example. And we have a more complicated example. This is we've done similar thing in the continuous sum case. So x over n equal to this linear combination sine and cosine, and sum of the sine and cosine invariant form phase. But here is a familiar algebra, so let's give most details. So sine can be written as the difference of complex exponential, and cosine is the summation of complex exponential. Cosine is the summation of complex exponential, and this HR pi over 2 phase term give you HR factor on your coefficient, so you get HI e to j pi over 2 here, and e to minus j pi over 2 here. And anyway, you collect the terms on your complex exponential, so your e to j 2 pi j omega naught n term has this coefficient from this 3 over 2 and this 1 over 2j, and and this e to minus j omega naught n term has coefficient from this 3 over 2 and this minus 1 over 2j, etc. And so you can read the coefficients from the expression here. So coefficient for k equal to 0 is this 1 here, and the coefficient for k equal to 1, so is this 3 over 2 minus 1 plus 1 over 2j, and you can write it as most standard form for complex number. And then this is the coefficient for k equal to minus 1, because it is minus 1 times j omega naught n. Okay, so a minus 1 is this thing, and you have a2 here and a minus 2 here. Okay, and ak equals 0 for other k if your n is larger. Okay, and so we plot this on a line. Once again, we plot the ak on a line as a function of k. But ak is now for complex numbers. So we plot the ak with the amplitude and ak with the amplitudes and phases. Okay? So and the angle. So this is, we are plotting ak as a polar coordinate. And you see we have 1, 2, 3, 4, 5 over the non-zero amplitude, and for a0 the angle is 0, but here you see that for a1, a minus 1 you have the angle, and the a2, a minus 2 you have the angle. And and it's periodic with period big N. And here we have some pretty large big N, maybe 10. Okay. Then let's see a more complicated example. And this example we'll see the convergence for the discrete-time Fourier series. Okay. So we go back to our familiar block wave. Okay, so this is a discrete-time analog of the block wave signal. So it's 0 everywhere except between minus n1 to 1 is 1, and it's periodic with some period big N that's bigger than twice n1. Okay, and so this is block wave signal, and remember that in continuous time case the Fourier series analysis is quite complicated, so you can write the Fourier series signal, but we see that it has those Gibbs lemma ripples. Okay, and maybe let's try to jump back something here. Okay, so in continuous time case, when we try to approximate the block wave signal, we see that the summing back we get this weird Gibbs effect ripple. Okay. But in discrete time case, we are going to see that there will be no convergence issue. Okay, so we can calculate AK, but now we do AK by brute force calculation here. So AK is summation begin and summing over one interval, summing over one interval, and instead of n we write n for because we want to do changeable variable later. But anyway, we summing over we sum over one interval, and x of n e to the minus jk, x of n times e to the minus jk to e to the minus jk omega naught n. Okay, and I guess here we already do changeable variable here. Okay, it's a bit annoying. Okay. So here we do the summation, but you see x of n is, so the m is actually saying we sum from this point to this point. So m is some point from, so m is basically n minus n1, okay, or n plus n1, okay, and yeah. So here I guess I should write down the changeable variable here. We are doing a bit faster. So we have n equal to n minus n1. Okay, so we do changeable variable. So x of n, and so x of n is 1 for this non-zero range. So x of n is just this thing. And then here we have e to the minus jk omega n, and we change n to some n minus n1. So that n is n plus n1, so n was from minus n1 to n1, and n was from 0 to 2 to the n. Okay, and yeah, and then we basically just do algebra. So you take out, so here is the summation of summation of m. So you take out the n1 term here. So it is quite small here. You take out this factor with n1 that has nothing to do with the summation. And then just do the summation with this geometric series formula. Okay, this is a geometric series with a power to the n, with something to the power of n. Okay, so you do a geometric series formula, and skip 2 steps of the calculation. And in the end, what you get is this sine over sine function. So you have this sine 2 by k n1 plus 1 over 2 divided by n over sine pi k divided by n. I guess here we should look at the most important variable here is k here, because this is basically a function of k, and the k is here, and so this is sine of something times k over sine of something times k. So basically, both of them are sine function of k, just with a different frequency. And the frequency up here is higher because it's both of them has this pi over n, but this is multiplied an extra 2 times n1 plus 1 half. Okay, so it's higher. It's a faster oscillation sine divided by a slower oscillation sine. Okay, and so this is for k not equal to 0 or multiple of n. That's when this upper k. This is for this. This is when the lowercase sine not equal to 0. And so when if k equal to 0, then this thing is you are just summing over a whole bunch of constant value here, and I guess it's even easier to see. When k equals to 0, then when k equals to 0, you are just summing over x of n divided by big N. So you are just having, you just have 2 plus n1 plus 1. So it's a number of non-zero spec here, and divided by big N from just this divided by big N. Okay. So when k equals to 0 or multiple of n, then your ak is 2n1 plus 1 over n, and when k is non-zero, you have this sine over sine. And anyway, what does this function look like is like this. Okay. And yeah, so it's once again it's a periodic function with a period big N. Okay, and we plug this for different big N. Okay. So we are fixing n1 equal to 2. So we are fixing the upper oscillation, the HR oscillation frequency, and we have a bigger and a bigger. Okay. So you see that is that so n equal to 10. So n equal to 10, n equal to 20, n equal to 40. So you see that you have this big period, and inside you will have basically phi oscillation corresponding to when n equal to 2, you have phi spike here. So you have this phi, I guess, minimum and maximum or minimum in one period. So it's 1, 2, 3, 4, 5. And similarly, you have 1, 2, 3, 4, 5 here, etc. And for n equal to 10, it's kind of hard to see, but you also have 1, 2, 3, 4, 5, like this. Okay. And yeah. So this is AK, and I guess it is NAK because everything divided by big N. So when big N gets larger and larger, this will be lower and lower. Okay, and yeah. Anyway, so this is what this sine over sine function look like, and it's periodic with period big N, and I guess we can go back to maybe here. Sorry, this is the lecture that we have even before. So in a continuous case, we have this thing. So in the continuous case, we have the AK being a sinc function, and it's like decaying out. It's not periodic. We have a sine k over k, and this 1 over k will decay out to 0 as k go to infinity. And different from what we get here, and this is periodic with period big N. Okay, because the lowercase is not basically sine k. Okay. And okay, 3 minutes, I guess we can finish here. And the thing I want to say is that there is no convergence issue for the discrete-time Fourier series. That is, when you add, so you have those AK, and you add them back with our synthesis equation, you will get your block wave exactly. And there is no convergence issue, and there is no Gibbs phenomena. Okay. So okay, so that's much slower than we expected, but we have 3 minutes. So I guess first, anyone has a question for the discrete Fourier transform? Otherwise, we can next time we will start from here again. But I guess because we were 3 minutes, we can show a bit of the length part because it's very short anyway. So just like in continuous case, next part we are going to show property of the discrete-time periodic signal. So the discrete Fourier series pair. So x of n Fourier series to a sub k, and we basically just give the result here. Okay, because most of the derivation the result are very similar to the continuous case. So you can see, let's try to get bigger here. Okay, you can see the linearity is basically the same. So you have x of n plus by of n, and the corresponding coefficient ck will be a times ak plus b bk. And time shift, you have similar thing. You do time shift on your signal, then you get this hr e to the minus jk omega n0 here, where this n0 is the shift n0. And frequency shift is similar, and conjugation and time reversal basically the same. So you do conjugation on your signal, then you get conjugation and minus k on your coefficient, and do time reversal, then you get basically also I guess frequency reversal on your series coefficient, so minus n, and you get minus k here. And just from these two things, you see that you can get the same real imaginary analysis, or the real imaginary or even other analysis on your Fourier series coefficient. So say if you have even signal, then you know that your Fourier series coefficient is also even. Okay, So the even odd of the Fourier series coefficient will be same as the even odd of the your signal that's sent either in that's either in continuous time case or discrete time case is the same. And okay, then we also have the convolution. The multiplication pair is very similar, but time scaling is different because I think we are going to detail about time scaling later. Okay, so so down here we have the conjugation symmetry for the real and imaginary thing. It's the same analysis. This real and imaginary or even odd analysis is the same as in a continuous time case, and the possible relationship is also very similar. And so we will focus on the different part that's next time. So like I guess the multiplication is a bit different, although I think it's very similar. And and the differentiation and the difference is different, and possibles is basically the same. Okay. And we don't have multiplication. Let me see. I guess time scaling is a bit funny because usually you cannot time scale a discrete time signal, and I think this kind of thing we'll talk about maybe in next chapter. Okay, and sorry, I think we are going over a bit over time, but next time we'll go over more detail about the property of discrete-time Fourier series, and we'll finish chapter 3 and start on chapter 4. Okay, where we'll talk about Fourier transform, basically for non-periodic signals. Okay, so see you next Monday.